All right, so as we've been talking about, we talked about stoichiometry, which is really sort of what we did here in this experiment. And remember, in a basic stoichiometry problem, like we did last time, and kind of like the experiment today's calculation, there's really 4 steps that you want to follow to do sort of a basic stoichiometry problem. Remember that you always want a balanced equation. And remember that if your equation is not balanced, then pretty much your entire calculation is going to be wrong because you're not going to have the right relationships. You want to take whatever they give you basically and convert it to moles. And usually what that entails is getting that unit into grams and then taking the grams to moles. Remember that it is the molar mass that is your conversion factor that allows you to do that, grams per mole. And that is again from the periodic table. Also remember, as we talked about, that if you need to calculate the molar mass, it is just based off the formula, no coefficients or anything like that. So just if you took one of the formulas by themselves, then you just add up the parts. Remember, we don't use coefficients for the molar mass. That's really the definition of it per 1 mole, so always just based off the formula. Number 3 is you're going to do the mole-to-mole relationship from the balanced equation. Remember that if you have a balanced equation like 2a plus 3b gives you 4c, you could use the coefficients as the mole-to-mole relationship. And you could say for every 2 moles of A, I get 3 moles of B needs to be put in there. Every 2 moles of A, I get 4 moles of C out. For every 3 moles of B, I get out 4 moles of C. These are equalities, really conversion factors that you can get from the equation. Remember, it's nothing more than just the coefficient. For each of these, you could get 2 conversion factors to use. You could use 2 moles of A over 3 moles of B, or you could flip it, 3 moles of B over 2 moles of A. And remember, you're not going to use all these conversion factors in a problem. You're just going to use whichever one you need to use to obviously get the calculation like you need it. Any questions on that stuff we talked about last time? Obviously, the 4th step here I missed, which is at that point, you should be done. You should always be in moles at this point after you do step number 3. A lot of times you need to convert it to some other unit. So very commonly we go moles back to grams is a very common conversion. And once again, you would use the molar mass again from the periodic table to allow you to do that. So really these 4 steps in a row is really your basic stoichiometry problems. So for example, like the experiment today, you weighed out a certain number of grams of Ki, you would convert those grams to moles. You would do the mole-to-mole relationship from the balanced equation between Ki and PbI2. And then you would use the molar mass of PbI2 to convert those moles into grams, and that would give you your theoretical yield. Remember that you could do stoichiometry relationships between reactants, between products and reactants. You could go anybody in the equation, you basically could use this relationship. Any questions on that there? Okay. So now that we talked about basic stoichiometry problems, we're now going to talk about another type of stoichiometry problem, which are known as limiting reagents. And what happens in a normal reaction is there is always a reactant that gets used up first, and there's always one you got plenty of. So there's always something that gets used up first and something you got plenty of. You can think of it like maybe if you ever bought hot dogs and hot dog buns. It's 4th of July soon, right? They give you 8 hot dog buns, right? But 10 hot dogs, right? So you never have enough to make a full package. You always have to buy more. So in a reaction, the idea behind limiting reagents is this. If you have A plus B that comes together to make A and B, and let's just say, for example, A was the limiting reagent. The limiting reagent is really important because it is the one that determines how much product you can make. So obviously in this simple example, I need an A and a B to come together to make my product. And at some point, I'm going to run out of A, which means there is no possibility I can make any more product at that point because I am missing, obviously, A to do that. So the limiting reagent is always the one that determines how much product you make. What is the other reagent? The other reagent is the one you got plenty of. That is what is sometimes referred to as the excess reagent. The excess reagent is the one that you have enough of. You'll actually have extra or leftover of that when the reaction's over. But whenever we want to calculate really how much product we're going to make, it is the limiting reagent that determines how much you make. For example, in the experiment you just did, you weighed out a little bit of solid, right? And then you put a bunch of liquid on it, right? The other reagent. The solid is your limiting reagent in that case. The other guy you had plenty of, and that it was your excess reagent. And that's why when we calculate the theoretical yield in this experiment that we just did, we base it off the solid that we started with because it was the limiting reagent in this reaction, okay? So as I mentioned before, the limiting reagent is the one that gets used up first. It is the one that determines how much of that product you're going to actually make. And obviously, the excess reagent is the one that you have plenty of. And again, you'll have that left over when the reaction is done. So if we take a look at this example, we have workout sort of buddies here. We have 5 women workout buddies and 3 guy workout buddies here. To make a partner, we need one of each. So this guy and this one team up, this one and this one team up, this one and this one teams up. At this point, I am out of guys in this case, right? I cannot make any more workout buddies together. And that would mean over here, this would be my limiting reagent. And this guy over here would be my excess reagent. We could also, in calculations, figure out how much of that excess reagent is left over. In this simple example, we could see we have 1 and 2 left over. And in a calculation, you could actually figure out how much is left over as well. So the limiting reagent is what prevents us from making more product. The good news about limiting reagent and excess reagent is this: you only need to be able to identify one of them, because then the other guy is the opposite. So if you can identify the limiting reagent, whatever else is there is the excess. If you're able to identify what's the excess reagent, then the other one was your limiting reagent. Now, let's take a look at this example here, and let's take a look at this reaction. And let's just say, for example, and I'll write a little bit higher in here so it's a little easier to see, I think, 4 moles of S and 20 moles of F2. All right, so let's say we have this reaction here, and we're going to start with this amount of each of those reactants, right? These are our reactants here. Now, what do you have to do in a limiting reagent problem that's different than a regular stoichiometry problem? There are multiple ways you can do these calculations. The way we're going to talk about it is we're just going to kind of do our same 4 steps. So we're going to still have to have a balanced equation. You still need to convert whatever they give you into moles. And right around here, you do need to do a calculation to determine which one is the limiting reagent. So after you convert everybody into moles, you do have to do a small little calculation to figure out which one's the limiting reagent. Once you do that, the rest of the steps are the same. You're going to use your limiting reagent and do your mole-to-mole relationship, and then convert those moles to some other unit. So it's really the same 4 steps, except we're going to insert a calculation to figure out the limiting reagent. So how do we do that? So first things first, how do I know this is a limiting reagent type problem and I should do this? The way you know it's a limiting reagent problem is you're given in the problem itself enough information to get the starting moles of each of your reactants. So if you're given enough information for you to calculate the starting moles of each of your reactants, then you know that you have to do a limiting reagent calculation. And by the way, it does need to be a calculation. You can't just look at it and go, that one looks smaller, I'm going to call that one my limiting reagent. It doesn't work that way. It does have to actually be done through a calculation. So that is how you know it. So if you think about all the problems we did yesterday and even the one maybe you did today, you weren't given enough information to get the moles of everybody. So it's just a basic stoichiometry problem at that point. That could be in this example here, obviously. We have the moles of each reactant given to us, so we don't have to worry about it. So we do have moles. So how do you figure out what to do? So we did the balanced equation. We converted everything to moles, which was already in moles. So now we're at this step here. And you do this step really two ways, but here's what you could do. You could choose either reactant. It doesn't matter which one you choose. So what I'm going to choose is I want to know how much F2 I need to use up all of my sulfur. So I'm just going to do a very short little calculation between sulfur and fluorine in this case. And what I'm going to try to figure out is how much fluorine I would need to use up all the sulfur I started with. So to do that, we're going to take the 4 moles of sulfur that I'm starting with. I'm going to go to the equation and find the mole-to-mole relationship between these two. And from the equation, we can see for every 1 mole of sulfur, we get 3 moles of fluorine, right? It's a 1-to-3 relationship. So opposites cancel. So 1 mole of sulfur on the bottom, 3 moles of fluorine up on top. I just did a very simple reactant to reactant calculation. And basically what that tells me is I have 12 moles of fluorine is needed. So that 12 moles of fluorine is how much I would need to use up all my sulfur. So this is how we now can determine if this is a limiting reagent or not. I need 12 moles of fluorine, right? How many moles of fluorine did I start with? I started with 20, right? So do I have enough moles of fluorine to do that? If I compare those two numbers, the 12 and the 20. The answer is yes, 12 is less than 20. So the answer is yes, I do have enough. And because you do have enough, what that tells you is the fluorine is the excess reagent because you have enough. And by default, the sulfur would be your limiting reagent. Any questions on that there? Now, just to show you that it doesn't matter which one you choose, if I did the opposite calculation, which in this case would be how much sulfur is needed to use up all the fluorine in this case. I'm going to do basically the same calculation, just reversed. So I'm going to start with my 20 moles of fluorine. I'm going to use my mole-to-mole relationship, which is the same. In this case, 3 moles of fluorine on the bottom and 1 mole of sulfur on top. The moles of fluorine will cancel. 20, I will pull some people's beakers in just a second. 20 divided by 3 gives me 6.667 moles of sulfur is needed. So in this case, if I did the opposite calculation, this calculation tells me I need 6.6 moles of sulfur. How many moles of sulfur did I start with? Only 4. I do not have enough, yeah? Started with 4 moles of sulfur, not enough. So that again tells me sulfur is the limiting reagent. And by default, the fluorine would be the excess. So you do not have to do both of those calculations. You could just do one, and it doesn't matter which one you choose. It will tell you the same thing, which one's your limiting reagent and which one's your excess reagent. Any questions on that there? Once I determine my limiting reagent, then I would go back to my starting amount, for example. I would go 4 moles of sulfur, and I would figure out how much product I would make. 1 mole of sulfur is 1 mole of SF6, and that would get me 4 moles of SF6. This would be my theoretical yield in moles in this case. Yeah. Any questions on that? So it's really the same 4 steps. You just have to kind of do that little calculation in the middle to determine which one's your limiting reagent. Once you figure that out, then the rest of the steps are the same. You use your limiting reagent. The important thing, though, use your starting amount of your limiting reagent here is what you want to use. Any questions on that there? Okay. And I'll just scroll through. This is basically what we just talked about. So why don't you try one here and see what happens, see what you come up with. We have a 6.8 grams of iron is allowed to react with 9.34 grams of sulfur. Which of the two are the limiting reagent, and how much iron 2 sulfide would you produce? Iron is 5585, I believe. And sulfur is 3207. So why don't you take a few moments and work that out. Again, follow the 4 steps. Balance the equation, convert to moles. You do need to do perhaps a limiting reagent, mole to mole relationship. And okay, let's go through it together, see how you're doing. Again, first off, I'm given 6.83 grams of iron, allowed to react with 9.34 grams of sulfur. Here's the deal. If I want to know how much product I'm going to make, and it didn't ask you which one's the limiting reagent, I do know this is a limiting reagent problem because I have grams of iron, which I could very easily get to moles, right? And I have grams of sulfur, which I also could get to moles. So that is the key thing that you're looking at, which is, can you get to moles with the information given to you of each of the reactants? And the answer is yeah, we could just use the molar mass to do that. So that tells me somewhere along the way, I do need to do this limiting reagent step to do this calculation correctly. But before that, I'm just going to follow the basic steps, which is balance the equation, which it is. So step number 1's good. Step number 2 is we do need to convert to moles. So we're going to take our 6.83 grams of iron. Going to use the molar mass there of iron. What's that? 5585, I think, grams per mole of iron. And that's going to give us our moles of iron to start with, which is 6.83 divided by 5585. Gets us 0.1223 moles of iron. We're going to do the exact same thing for the sulfur, 9.34 grams of sulfur. Going to use the molar mass from the periodic table of sulfur, 3207 grams per mole. Going to go 9.34 divided by 32.07. Going to give us 0.2912 moles of sulfur. Again, if it helps you, you could label this as like your starting amount of each of those. Yeah, so you could kind of keep it straight. Now, a very common mistake that people make is they do this part and go, cool, it's always going to be iron in this case because it's a smaller number. That is not always the case. So it is not always the smallest number that you see there. A lot of times it is, but it's not always. So it does have to be found through a calculation. So I'm going to choose, and again, it doesn't matter which one you choose. So I'm going to choose how much sulfur I need to use up all my iron. So I'm going to choose how much sulfur is needed to use up all the iron. So to do that, I'm going to start with the iron. that I started with, the 0.122 moles of iron. I'm going to do a mole-to-mole relationship between iron and sulfur, which from the equation, every 1 mole of iron gives me 1 mole of sulfur. That gives me 0.1223 moles of sulfur is needed in this case. Again, those we're going to cancel. At this point, what I want to compare is how much is needed to how much I have to start with. And again, I need 0.122. I have 0.29 to start with. So I do have enough. And because I have enough, that's all I need to figure out. That tells me sulfur is my excess reagent. And by default, that would mean it is the iron that is my limiting reagent. And that is the purpose of that little calculation, is to basically figure that out. Any questions on that calculation there? Now that I have figured out the limiting reagent, remember that is the one that determines how much product you make. So I'm going to now start with my limiting reagent, the starting amount, and now figure out how much product I made. So I'm going to go now with my starting amount of my limiting reagent. I am now going to do a mole-to-mole relationship between my reactant and my product. And that would give me 0.1223 moles of my product. This would be, again, my theoretical yield in moles. But I want grams, so what I'm going to do then is I need to do step number 4 now, which is the molar mass. So the molar mass of iron and sulfur is just adding these together. So 5585 plus 3207 gives me a molar mass of 8792 grams of iron 2 sulfide per mole. The moles will cancel. And that would get me about 10.8 grams of iron 2 sulfide. That would be my theoretical yield in grams. So that would be my theoretical yield in grams. Again, it really is the same 4 steps with just a little bit of a limiting reagent sort of step in the between. Again, it is step number 1, balance the equation. Step number 2, convert to moles. Limiting reagent calculation. Step number 3 and step number 4, basically. So same 4 steps, just with that inserted in there. Any questions on any of that? Now, I will tell you there are multiple ways you could do this type of problem. And a very common way that people are taught these days is to actually just do 2 separate calculations. And what I mean by that is you would do a calculation starting with the iron and figure out how many grams of the iron 2 sulfide it would produce. Then you would do a separate calculation where you start with the grams of sulfur and figure out how many grams of the iron 2 sulfide it produced. Whichever one produces the smallest number of grams is the limiting reagent, and that's the way, another very common way it's done. I personally don't care if you like that way better. You see it in the book. That's a super common way they teach nowadays, but this is a good way as well. So there's actually like 3 or 4 different ways you can actually do these type of calculations. Any questions on that? Now, can I figure out how much of my excess reagent is actually left over at the end of the reaction? The answer is I actually can, based on the information I got. I know that I needed to use up this much of my excess reagent, and I know this is how much of my excess reagent I started with. So to figure out how much of my excess reagent's left over, actually I'll do it up here so it might be easier to see. Let me just erase some of this here, actually. Up here. I can maybe see it. So if I take the moles of my excess reagent I started with, which was 0.2912 moles of sulfur I started with, I needed from this calculation 0.1223 moles. of sulfur. And if I subtract that, that will give me 0.2912 minus 0.1223. That would give me 0.1689 moles of sulfur is left over. I then can multiply that by the molar mass of sulfur, which is 32.07 grams per mole. And that will tell me how many grams of the sulfur was left over. And in this case, it was like 5.42 grams of sulfur was left over. Remember, I started with about 9 grams of sulfur, and I have about 5 grams left over. So in this reaction, I use a little under 4 grams of sulfur in this reaction. In terms of the iron, which is the limiting reagent, I should have none left over at this point, right? It all should be used up. Any questions on that there? All right, so let's try another one here, maybe. I'll scroll this across. This is what we just did. All right, so why don't you give this a go, see what you come up with. So basically, we want to know how much product we're going to produce, which is this guy right here. How many grams of it? And they did give you the molar mass, so you don't even have to calculate it. So we have... Okay, let's take a look, see how you're doing. So once again, the key things that you're looking for, once again, we are given the grams of each reactant. So right off the bat, I know I could get to the moles of each of these guys. So that again is the key, that this is a limiting reagent type of problem. So that is what you want to look at. If it is not a limiting reagent problem, it's just a basic stoichiometry problem, those 4 steps without the limiting reagent calculation, you can just roll right into it. But here you do know you need to do that. So we're just going to follow the same steps really as before. We're going to balance the equation, which it is balanced in this case. We're going to convert to moles. So we're going to take our 622.7 grams of NH3. We're going to use the molar mass of NH3, which is 1703 grams per mole. By the way, if that was not given to you, you would have to get it from the periodic table. And here we're going to go 622.7 divided by 1703. That's going to give us 36.565 moles of NH3. We're going to do that for our CO2 as well. We're going to divide by 4401 grams per mole, which again comes from the periodic table. And if it wasn't given to you, you would have to calculate it yourself. 1241 divided by 4401. That's going to give me 28.198 moles of CO2. Once again, this is going to be our starting amount. And now, because we know it is a limiting reagent type problem, we will need to do that calculation. So as we talked about previously, you could choose whichever one that you want. I'm going to figure out how much CO2 is needed in this case to use up all of my NH3. So I'm going to take the moles of CO2, 28.198 moles of CO2. I'm going to do, I'm sorry, I chose the wrong one. Let me start with the other guy there. I'm going to take my NH3. That's what I want to use up. So I'm going to take my 36.565 moles of NH3. I'm going to do a mole-to-mole relationship between these two, which is a 2-to-1 relationship. So for every 2 moles of NH3, I get 1 mole of CO2. The moles of NH3 are going to cancel. That will give me 36,565 divided by 2. That tells me I need 18.28 moles of CO2 is needed. Remember, this is the point where we're going to compare to how much we started with. So I need 18 moles. I started with 28 moles. I do have enough when I compare them. That means that this is my excess reagent. And by default, it would mean that my limiting reagent is the NH3. Any questions on that calculation there? Now that I know my limiting reagent, that is important because that is the one that determines how much product I'm going to make. So I'm going to come back to my starting amount of my limiting reagent and now figure out how much product I'm going to make. So we will go with our 36.565 moles of NH3, which is our limiting reagents. We're going to now do a mole-to-mole relationship between our limiting reagent and our product, which is a 2-to-1. So for every 2 moles of NH3, we get 1 mole of NH2CO. Those are going to cancel, and that will get me 36.565 divided by 2, 18.283 moles of our product. This again would be our theoretical yield in moles, but we're interested in grams. So we're going to do our fourth step, which is our molar mass, which was also given to us. 60.06 grams per mole. And those moles are going to cancel, and that will tell us that we would produce here about 1,098 grams of our product. Since we are a chemistry class, maybe we're interested in sig figs, but that's about 4, so we'll go with that, I suppose. Any questions on that? So once again, same 4 steps: balance equation, convert to mole, has to do a limiting reagent in this case, step number 3 and step number 4. So hopefully you can see a pattern here of what you need to do. Once again, you could also not get an answer in between, just go straight through and do it all as one calculation. Any questions on that there? All right, let's take a look then. And I'll scroll this across what we just went through. And I didn't do it, but you could, just like the previous one there, figure out how much of your excess reagents left over by looking at that calculation. In this case, we would have 437 grams of our CO2 left over. All right, any questions on that there? All right, I'll pull everybody's stuff in 1 second. Yields of reactions, the next thing we're going to talk about. So as we just talked about and kind of did in this experiment as well, there are 3 types of yields that we come across. The first type of yield is the theoretical yield, and that's basically calculated based off of the equation and how much you started with. So like in your experiment, like I said before, like the 0.4 grams that you weighed out, based on the calculation, you could calculate how much product you should have made. That number of the theoretical yield is actually the maximum amount of product that you should make if everything went perfect. There was no side reactions, you didn't drop anything, you didn't lose anything on your stirring rod, for example, any of those type of things. That is the maximum amount of product you should actually make. The actual yield is the actual amount of product that you make when you did the experiment. Our example here, the yellow on the filter paper, that is your actual yield of your product in this experiment. In a textbook sort of problem, they will give you the actual yield. They'll somewhere tell you, in this experiment, you made this much of it. So they'll actually usually give you the actual yield in the problem. The theoretical yield, you usually need to calculate. This is usually given to you in a problem, the actual yield. By the way, a yield is always a product, right? So if you yield something, that's the right-hand side of the arrow. It has to be a product. Putting both of those together give us the important sort of yield, which is the percent yield. And you take the actual divided by the theoretical times 100. Your idea here for percent yield is a high number, like 100 or less than 100. Do you want a really high number, like over 100? Is that good in this case, you think? It is not. It actually means you screwed up somewhere, right? So you could get, for example, over 100% yield, and usually it means something didn't go right. A lot of times, for example, like the experiment we did, a lot of years we don't use the oven, and we just like throw it in our drawer and let it dry naturally. And if you didn't let it dry completely and you re-weight it, you would have a bunch of water weight that's not your product, right? It's just the water weight that's on the filter paper, and that's what would cause you to have like over 100% error. So you do want to be near 100%. You don't want to be way over 100%. You know, in the 95% or so, that's a really good yield in most cases. All right, so why don't you try one here? Actually, let's skip this one. Let's try. Let's scroll through this one here, actually. Let's do this one. You take ammonia, 100 grams of ammonia, and react it with 100 grams of carbon dioxide, and you produce 120 grams of our product. What is the percent yield? These are the same ones we just did in the previous problem. NH3 was, what was that, 1703 or something like that, grams per mole. CO2 was 4401 grams per mole, and our product molar mass was 6006. I feel like I have that number in my head, 6006 grams per mole. All right, so give it a go here. We're looking for the percent yield in this case. All right, so once again, when we look at this problem, we do know it's a limiting reagent problem because I have the grams of ammonia and I have the grams of CH2 or CO2. And that means that I could get to moles of each of those guys. And that again is the key. I could get to the moles of each of my reactants, which means it is a limiting reagent problem. We're basically just going to do our same 4 steps with an additional kind of middle calculation. So again, step number 1 is to balance the equation. And that is right here, and it is balanced already, so we don't have to worry about that. Step number 2 is to take what they gave us and convert it into moles. And I do need to do that because I have 100 grams of each of those guys. So I'm just going to get rid of this so I have a little bit more room. So step number 2 here is convert to moles. So I'm going to take my 100 grams of NH3. Once again, I provided you the molar mass, but you might have to calculate from the periodic table. We're going to use 1703 grams per mole of NH3. We will do the same calculation with our other reactant, our CO2. We will take the grams and convert it into moles using the molar mass from the periodic table, 4401 grams per mole of CO2. And if we do that there, we will end up with 100 divided by 1703. Going to give us 5.872 moles of NH3. We're going to take the 100 and divide it by 4401, which will give us 2.272 moles of CO2. Once again, a reminder, it might help you just to label these guys as your starting amount so you can kind of keep everything straight. Now remember, because this is a limiting reagent problem, we do have to do the calculation to figure out which one's the limiting reagent. So you could choose either reactant. It does not matter which one you choose. You could choose either one. I'm going to choose my CO2 and figure out how much NH3 I need to use it up. So I'm going to start with my 2.272 moles of CO2. I'm going to do just a really quick calculation between these two. And from the equation, I can see that for every 1 mole of CO2, I get 2 moles of NH3. So this is a basic little stoichiometry calculation using those coefficients. And if I do that, I'm going to multiply that by 2, and that would get me 4.544 moles of NH3 is needed. In this case, I would then compare it to the amount of NH3 that I started with, and I did start with 5.8, and I only need 4.5, so I do have enough. And because I have enough, that means the NH3 is my excess reagent. And by default, the limiting reagent would be my CO2. Any questions on how I determined that there? Once again, you could have did the NH3 and figured out how much CO2 you needed. Should come out basically the same in terms of which one's your limiting reagent. And you would see, for example, if you did the other one, you need 2.9 moles of CO2, but you only have 2.2, so you do not have enough. The point of that calculation really is to allow us to know which one we should use to figure out how much product we're going to make. So now that I know CO2 is my limiting reagent, I'm going to use the moles of my limiting reagent and really just do step number 3, which is 2.272 moles of the limiting reagent. And now I'm going to do a mole-to-mole relationship between my limiting reagent and my product, which is a 1-to-1 relationship. 1 mole of CO2 gives me 1 mole of my product. Now, in this case, I'm going to use the molar mass of my product to convert it into grams. And from the periodic table, it is 60.06 grams per mole of my product here. The moles are going to cancel. Moles are going to cancel. Going to leave me grams. That will tell me 2.272 times 60.06 will give me about 136.5 grams of my product. And that would be my theoretical yield. Yeah. First off, any questions on the theoretical yield? Once again, same 4 steps. Step number 3, step number 4 there, yeah. The actual yield was actually given to us in the problem, so I kind of wrote over it. But if you look back in the problem, it said we produced 120 grams of our product. So that 120 grams of our product, which was given to us in the problem, is our actual yield. And that is going to allow us now to calculate the percent yield. The percent yield in this case, maybe I'll do it up on top so you can see it. I know this room's a little hard to see in some places. So let's get through that. There we go. So our percent yield in this case would be our actual yield divided by our theoretical times 100%. Our actual, which was given to us in the problem, was 120 grams. Our theoretical was 136.5 grams, times it by 100%. And that's going to get us about 87.91% yield. Not terrible. Any questions on that there? So percent yield, actual yield, theoretical yield. Theoretical yield always comes from the equation and how much you're starting with, and that's your maximum amount of yield. Actual yield in book problems will be given to you. In our lab here, obviously, it's your mass of the yellow solid that's on your filter paper. Divide the 2 times it by 100, and you should get your percent yield, which ideally should be high number, but not over 100. You may have a little over 100 in the lab, but ideally shouldn't go much over 100. Any questions on any of those steps there?